In this lecture, we will talk about diffusion. So far, we had mentioned diffusion on and off in the earlier lectures. Essentially, diffusion is migration of atoms, whether it's in the in a gas, or migration of atoms in a liquid, or migration of atoms in a solid. So diffusion takes place, or movement of atoms takes place in gases, liquids, as well as solids. Regarding gases and liquids, we have an intuitive idea of movement of atoms, because from our everyday experience we are able to tell that atoms do migrate very easily in gases and liquids. If we drop a colored dye in water, you will very quickly see the color spreading, which means the dye, the atoms that make up the dye very quickly move in the liquid medium. Same thing happens with gases. If you you can easily smell any thing like let's say a chemical bottle opened up in one corner of the room, very quickly you will smell it at the other end of the room. However, in solids, we don't have direct experience until we actually measure the movement of atoms inside a solid. For example, if I take a block of copper and I weld it, join it with a block of nickel, let us say. So, I have copper here, pure copper, I have pure nickel here, and if I look at how the copper atoms and nickel atoms are distributed across this couple, copper nickel couple, that is, let us say here it is concentration of copper atoms, then when I join it in the beginning, I will have some 100% copper on this side. So, I will have concentration of copper as, let us say, fraction of copper atoms is 1, and in the nickel side there will be 0 fraction of copper atoms. So, this is at, let us say, time t equal to 0. If I measure it after some time, but if it was at, let us say, room temperature, then we would see no measurable change. However, at an elevated temperature T, if I measure it after some time T, if I expose this couple, put this couple inside a furnace for some time and then take it out and then measure the copper concentration right across, I may observe a concentration profile of copper like this, basically telling me that copper atoms have migrated to the nickel side. Similarly, if I were to make a concentration profile for nickel, I will observe the reverse situation where nickel atoms may have migrated on the left hand side. So, this is what we would call as diffusion in the solid state. So, in this lecture and subsequent lectures, we are going to be concerned with diffusion of atoms in the solid state. In fact, it took several decades to really understand how diffusion was taking place in the solid state, where atoms are very compact and there is hardly any place to move. Even then diffusion takes place. So, the exact mechanism of movement of atoms is now well understood, and that is what we will be looking at. But before I go into diffusion in the solid state, I would like to just in general, if there was an atom which could migrate in any direction, then, and in fact if it does not have any preference to move in a particular direction, then we have a problem which is called as the random walk problem. This is also often called as the drunken walk problem or Brownian motion, where particle could move in 3 dimensions in any direction. It can we can look at such a problem in 2 dimensions. We can also look at such a problem in 1 dimension. Just to show you a little bit of an animation, consider a 1-dimensional random walk where you have an atom located at the origin and it is constrained to move only along this axis in 1 dimension, either in the plus direction or towards the left in the negative x direction. If we let this atom move, and at every step there is an equal probability for this atom either to move in the plus direction or the minus direction, plus it moves in steps of lambda. In that case, as you can see, this atom has moved 2 steps, 3 steps, it can go back, well it has gone forward to 4 steps and then it can reverse, and the problem could be that after how many steps, what will be the location of the atom after an x number of steps. A similar situation one can also see in 2 dimensions, where again the atom is now free to migrate in 2 dimensions, so it can move up and down and left and right, and the problem that we want to look at is that after it has travelled some n number of steps, where would this atom be located. So, we will try to solve this problem as a 1-dimensional problem and see what is its significance in the case for diffusion. So, let us consider a 1-dimensional walk. So, we will look at a 1-dimensional walk problem, and it is constrained to move on this horizontal axis towards the right or the left, and let me break this axis up into steps of lambda. So, each time an atom located here can move in steps of lambda, which could be, for example, if it is an atom, simply an atomic step or the interatomic distance in solids. Here on this side it is minus lambda, minus 2 lambda, minus 3 lambda, minus 4 lambda and minus 5 lambda. Let us say that I want to look at where will the atom be after 1 step. So, after 1 step, if I have to look at this problem after 1 step, I want to see what path it will take and what will be its final location or final position. And the path it takes will determine what will be the position of this atom after 1 step. So, very clearly one possible path is it moves a step of plus lambda, which means this moves in the right direction. The final position clearly would be over here, which is simply plus lambda. It could move also in the negative direction by a step of lambda. So, the path it will be taking would be minus lambda and the final position would be minus lambda. Since we have assumed that there is an equal probability at any stage for this atom either to move in the right direction or the left direction, which means probability P of this atom being located at either plus lambda or minus lambda after 1 step is simply equal to half. That is, there is a probability of it being located at plus lambda is half, probability of the atom being located after one step at minus lambda location is also half. Now let us take this problem a step further and say what would be the atom position after 2 steps. Well, after 2 steps, again let us consider the path as before and the final position for each path. One possible path is plus lambda, so atom moves from here towards the right one step, and again plus lambda, so it moves another step of lambda, reaching the final position of 2 lambda. A second possible path plus lambda, and so it moves here and then it moves to the left by minus lambda. Very clearly it will come back to its starting point or 0 position, so the final position is 0. A third possibility, it first moves towards the left by a step of minus lambda and another step of minus lambda, so it reaches minus 2 lambda. A fourth possibility takes a minus lambda step and takes a plus lambda step, reaching the final position of 0 again. If I look at what is the probability of this particle would be at its starting position or the position 0 after 2 steps. So, there are 2 possible paths in which lead to the position of 0. So, there are 2 paths and there are a total of 4 possible paths for 2 steps. So, the probability would be 2 upon 4 or simply half. Probability that the atom would be at plus 2 lambda or minus 2 lambda after 2 steps for each of them. So, for the particle to be at plus 2 lambda position, there is only one possible path out of 4 possibilities, hence it is 1 upon 4, and similar is the case for the final position of minus 2 lambda. So, for plus 2 lambda or minus 2 lambda, the probability is 1 upon 4. Extend this further, what happens after 3 steps? Again we have to list down all possible paths, and clearly as we increase the number of paths, possible paths also increase. So, the first possibility, let me write down plus lambda step, another plus lambda step, a third plus lambda step. Clearly the final position would be plus 3 lambda. Second, plus lambda, minus lambda. So, it moves 1 lambda, another lambda, reaches 2 lambda, but then it returns back by a negative lambda. So, the final position is plus lambda. Third one, plus lambda, minus lambda, plus lambda. So, it starts from 0, it goes plus lambda, then comes back minus lambda, it goes back to plus lambda. So, the final position is plus lambda. Fourth possibility, plus lambda, minus lambda, minus lambda. So, it moves lambda, then it returns back and then goes further to the left by another step of lambda, reaching to minus lambda. Are there any other possibilities? Yes, all our first 4 paths started with a step towards the right. Now, I can just repeat this whole exercise for all steps beginning with minus lambda, or the particle moving to the left as the first step. So, minus lambda, again minus lambda, again minus lambda, that gives me the final position as minus 3 lambda. Then I have minus lambda, and a plus lambda. This will give me the final position to be minus lambda. Another possibility, minus lambda, plus lambda, and let us say minus lambda. So, minus lambda, plus lambda, minus lambda, giving me final position of minus lambda. Then I can have minus lambda, plus lambda, and plus lambda. So, minus lambda, plus lambda takes me to the final position of lambda. If I look at it, basically after 3 steps, the only possible positions for the particles are plus or minus lambda and plus and minus 3 lambda. So, probability for the particle to be at plus or minus lambda after 3 steps would turn out to be, well, let us see for plus lambda. There are total of 3 paths which will lead to the plus lambda position. How many paths are there? If I count them, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 paths, hence the probability is 3 by 8 to be at plus 3 lambda, and the same, or to be at plus lambda, the same would be the case for minus lambda, the probability would be 3 upon 8. Similarly, probability for the particle to be at plus or minus 3 lambda after 3 steps, well, there is only one path which can take me to plus 3 lambda, there is only one path which can take me to minus 3 lambda. Hence, the probability is simply 1 upon 8 for each of the 2 cases of plus 3 lambda and minus 3 lambda. Similarly, one can determine for higher number of steps, and in fact one can generalize this to n steps. Now, what do we do with this? Well, I want to have an idea where would the particle be located after a given number of steps have been executed. So, let us look at it. Let me write down, make a table here, number of steps and average distance. Average distance moved by the particle from its starting location. So, if I calculate for just one, then what I have to do is the atom moves by this final position is plus lambda, therefore, the distance moved is plus lambda. So, in order to calculate the average distance, I will multiply by the probability multiplied by plus lambda, plus it can also move to minus lambda. So, again it has a probability of half multiplied by minus lambda. Very clearly, this just simply gives me 0. If I repeat this with the number of steps being 2, well, the particle gets located at 0 with a probability of half. So, half multiplied by 0 distance travelled plus half 1/4. There is a probability of 1/4 that it will be located at plus 2 lambda, giving from here. So, it is 1/4 into plus 2 lambda plus 1/4 into minus 2 lambda. Clearly, this is again, it gives me a result of 0. In fact, if I repeat this exercise for 3 steps, also the average distance moved would be 0. Similarly, if I go n steps, the average distance is 0. Now what does this mean? All this is telling me is that this only gives me an average distance travelled, but this does not mean that the atom will remain at 0 location. In fact, there would be a distribution of atom positions around the mean of 0. So the mean of the distribution is 0, but after a certain number of steps, this particle can be located at any position around the mean with a certain probability. So in order to take care of this problem, what we need to concern ourselves is with the mean square distance. So we should concern ourselves with the mean square distance. And what is the mean square distance? So let us calculate again. If I have here number of steps and the mean square distance, which is x square bar. So after one step, what is the mean square distance? It is half plus lambda square, the square of the distance moved, plus probability of half that it can be located at minus lambda. So it will be square of minus lambda, and this will give me a mean square distance of lambda square. After 2 steps, we repeat this. There is a probability of half that it is back to its starting position. So half times 0 square plus 1/4 times 2 lambda square, because that is the probability of 1/4 that the particle will be located at 2 lambda distance away from the starting point. Similarly, again a probability of 1/4 that it is located minus 2 lambda from the starting point. So it is minus 2 lambda square times the probability 1/4. If I add all this up, I will get 2 lambda square. So here I have lambda square, I have here 2 lambda square. After 3 steps, I leave it to you to calculate from these probabilities and these locations of plus minus lambda and plus minus 3 lambda. I will get 3 lambda square. So this tends to suggest the sequence. After one step, I have a mean square distance of lambda square. After 2 steps, I have a distance of 2 lambda square. After 3 steps, I have a mean square distance of 3 lambda square. Therefore, after n steps, the mean square distance would be n times lambda square. In fact, what this quantity that we have calculated is actually the variance of the distribution of positions. Since the mean is 0, x square bar represents the variance of this distribution. From this, I can also calculate what is the root mean square distance. The root mean square distance is simply, I will call this as x bar, which is square root of the root of the mean square distance, x square bar, which take the square root of this, and this would give me lambda times the square root of n. So this is the root mean square distance, that after n steps the particle is at a root mean square distance of lambda square root n. Now, if we assume that the jump frequency of the atom, after all, if I want to understand after how much time what would be the root mean square distance, I should know at what frequency the particle is jumping from one location to another location in steps of lambda. So, let us say that nu prime is equal to the jump frequency. So, it has units of per second, that so many jumps would take place every second. So, after time t, the number of jumps that would have taken place is nu prime t jumps. Now, this is nothing but n steps that a particular particle or an atom has taken. So, n is equal to nu prime t, which I can now substitute here, giving me the root mean square distance of lambda square root of nu prime t. This x bar is like a diffusion distance. And one notable thing from this relation is that this diffusion distance is proportional to square root of time. And this is an interesting conclusion that has been drawn here, that the diffusion distance is proportional to square root of time, and in fact large number of, in fact in all diffusion problems you are going to get this, that diffusion distance is related to or directly related to square root of time. This is one peculiar nature of diffusion. We will eventually relate this diffusion distance to what is called as the diffusion coefficient. If you remember, if you go back a few lectures back, I had talked about diffusional growth. In diffusional growth, I had brought in what was called as the diffusion coefficient d. And in fact, we would spend some time in the subsequent lectures on d and how this d is going to get related to this jump frequency. That means we will also have to understand this jump frequency, its nature, what all factors it is going to determine on. In fact, one of the factors that this jump frequency will determine on is again that when a jump takes place, atom has to go through a energy hill. So, it has to, just like in the case of nucleation, a stable nuclei had to form by climbing over an energy hill. Similarly, an atomic jump that takes place also has to climb over an energy hill, and therefore each jump would have a certain probability which would be linked to this jump frequency, as we will be seeing in the subsequent lectures. So, in this lecture I have given you an idea of diffusion. I have not yet brought in how diffusion will take place in the solid state. One has a good feeling that in liquid there is a lot of space between atoms, and therefore if I put in a foreign atom, that atom can move in between the spaces. Now, how exactly these jumps are going to take place in the solid state would be the subject of the next lecture. So, I will stop here.